Welcome to Insights Engineered. I'm Ethan Simon, Global R&D Director of Laird Performance Materials, a DuPont business. Laird enables and protects sensitive electronic components that enable the world's most sophisticated devices and machines. In this series, we speak with our brightest minds who are developing innovative ways to mitigate electronic magnetic interference and to improve thermal management in high power and high frequency electronic devices. Today I'm delighted to be joined by Paul Dixon, staff scientist, and Matt Tapping, sales manager, to discuss the 5G area, challenges, trends, and solutions. Welcome, Paul and Matt. Let's start with the basics. There's lots of press about the use of 5G to improve the mobile phone experience. What other benefits of 5G networks are you working on with your customers?
If we look just at 5G, the average person tends to think of smartphones. That's just one part of it. So with the Internet of Things, you need the 5G system as a network for transferring the data and collecting the data. It also allows you to connect devices as well. So there are rumoured to be somewhere around 50 billion Internet of Things sensors and devices that are interconnected within the next few years. So this is going to enable a huge number of possibilities which we're only just starting to imagine at the moment. The 5G network itself is used for actually collecting the data. So you will have sensors on multiple different devices. So at the moment it's mainly smartphones, and we're starting to see things like active speakers or connected devices in the home. So for example, lighting or possibly domestic appliances that you can control remotely. So each of those will have a sensor that's then connected. The 5G section of the Internet of Things is actually how we get that data from the devices back to where it can be used and what we can actually do with that. So the 5G network itself is made up of two sections. There's a backhaul section that connects the mobile data to the wired side of it, and then there's a front haul section, which is the part that does all the work. So basically this is connecting to the individual sensor, taking data from the sensor, pulling it back through the system, and then back to a data center, which then conglomerates the data and sends it on to wherever it's needed to be stored. So without the two of those, the Internet of Things basically wouldn't exist. And the kind of big driver for the Internet of Things is latency. So effectively how long it takes to read data off a sensor, get the data back, and do something with it. So latency, typically you're looking at millisecond ranges. So typically around 8 to 12 milliseconds to get the data from the sensor back to where it's going to be processed and to actually do something with it.
Can you give us an example of a real-world example of an application where low latency in a 5G network may be critical for it to function?
Right now, latency of 3G systems is about 10 milliseconds, which is the time between you make a command and act on the command. The goal for 5G is to reduce that to 1 millisecond. Now, milliseconds sound real short, but an automobile will go about a foot in 10 milliseconds. So any kind of involvement in automated driving, perhaps, would be greatly helped by reducing that latency. Also, large industrial machines, 10 milliseconds is not good enough. You need the short latency to remotely control these machines.
Thanks. Those are great examples. Matt, maybe you can tell us more about 5G networks and the mesh network and things like that.
If we look at a 5G network, we can think of it as being analogous to a human body in some ways. So effectively, you have the section which is taking information from the user or from the sensor. So for example, taking information from a smartphone call. That would effectively be like the fingers on a hand. And this in a 5G network would be managed by something called picocells or femtocells. So basically very small cellular networks, typically inside a building. So they would be handling data on a very small level. This data is then forwarded on to larger network sections, which would be, for example, the microcells or the metrocells. And this would be the kind of wireless connector systems you see in things like shopping malls or inside an office, for example. So it's typically a piece of equipment about the size of a sheet of paper, typically with a few antennas on the side of it. those data collection points are then aggregating the data that they've collected, and they're then moving it back to the next stage up, which would typically be a metro cell or to a MIMO antenna array. So these are typically the type of large antennas you see either on the outside of buildings or on remote radio masts. And the data from there is aggregated again, and then that's sent through to the data center for the 5G system. The data center then forms the part of the backhaul system which connects the mobile side of the 5G network to the wired side. And at that point, the data is then transferred from the data collection center to wherever it's needed in the cloud. So typically this would take the form of a server storage center, which is usually full of several hyperscale size servers. And it's then used from there for whatever the data is needed for or stored.
Do you think that MIMO antennas represent one of the largest challenges for thermal and EMI issues in 5G?
Yes, at low frequency, as Matt said, in a typical antenna might be an 8x8 array, 64 antennas with their associated power amplifiers, analog to digital converters, that sort of thing, that are all and about the size of a deck of cards or smaller. So it's just an enormous heat generation device. You know, sometimes it's this nice small antenna, but it's got this enormous heat sink attached to it, so kind of, and that needs to be hoisted up on a pole somewhere. So a lot of issues with that. The better we can disperse the heat, and the better we can solve the EMI problems as well.
Yeah, there's another side to this as well. So there's one thing designing an antenna system and making sure that you've got the crosstalk under control and getting the heat out of it. But the thing is, with these systems, they really need to be reliable as well over a long period of time. So typically, when we're talking to companies who are designing equipment for the networks, the system's designed to be installed, and then it probably won't be touched for another 10 or 15 years. So that there's a huge reliability aspect that comes into this as well. And effectively, that's what our materials are doing. You're buying insurance against the component going wrong.
So in the 5G area, what are some of the common thermal and EMI challenges that are driven by this transition to 5G?
Well, in the biggest transition in 5G is higher data rates. Everybody wants more data faster to more devices, that sort of thing, and that comes down to the spectrum. Generally, 4G, 3G systems are what we call sub-6 gigahertz, so it's low-frequency spectrum, and you need more spectrum in order to send more data, and that area sector, the sub-6 gigahertz spectrum, is already accounted for. So 5G is going to expand up into what we call the millimeter wave spectrum, above 18 gigahertz, specifically 28 gigahertz, 39 gigahertz, and others. As higher frequencies, shorter wavelengths create some severe EMI problems that cannot be solved by traditional methods. When I say traditional methods, generally shielding methods, do not work as well at those frequencies. So new solutions need to be found to solve the EMI problems. Another impact of the shorter wavelength is devices are smaller. In general, it's a good thing. Devices are smaller, but they kind of have the same functionality. So with ICs generating heat, so you get the same amount of heat in a substantially smaller area. So there's much greater thermal issues. And now EMI and thermal, they kind of compete with each other. With EMI and shielding, that sort of thing, they're just trying to contain energy. With thermal, you're trying to release energy. So solutions can fight with each other. So you really need to look at a multifunctional.
So all in a smaller space too, getting more and more compact. So how are we going about solving some of these challenges? Well,
we're looking at like what I call multifunctional solutions, integrated solutions, that sort of thing. It used to be, here's your EMI, fix, and here's your thermal fix. Might be the same company, might be a different company, but then sometimes solving an EMI problem creates a thermal problem. Solving a thermal problem creates an EMI problem. So we take the multifunctional approach that we need to solve both of them. One particular device or material is CoolZorb. That's a thermal interface material which conducts heat away from a chip, but it also absorbs electromagnetic interference energy. So it absorbs EMI, conducts heat. So it's one material that performs two key functions. So that's just one example of integrated solutions, multifunctional solutions.
So Paul, how how do we get there? What sort of tools are you using now to design these materials?
Well, from an electromagnetic point of view, which is mostly my field, we use some advanced electromagnetic modeling software to analyze how material will work in a system. And in order to do that, we need to measure that material, garbage in, garbage out, if you don't have the correct measurements of the materials. So we do that up well into the millimeter wave range, up to 90 gigahertz. For the thermal side of it, we do thermal modeling, where we can model what the temperature drop of a particular configuration is. And this reduces the design cycle time. So we're not making something, testing it, making something, testing it. We can reduce the total time to come up with a solution by using electromagnetic modeling, thermal modeling, and characterization of materials.
Mm-hmm. Makes sense. What are some of the other innovations you're working on related to these multifunctional solutions or the manufacturing process and so forth?
Well, one thing I'm working on here in Cleveland today is how to characterize the CoolZorb material in a specific application, rather than just saying, "Hey, here it is. Absorbs energy and does all these great things." We can measure it in an actual configuration, measuring the antenna descents, the reduction in antenna desensitization. We can solve using CoolZorb. So we're kind of zeroing in on exactly what is the most important properties of the material.
Matt, what are some of the innovations you're most excited about related to this space that we're making?
Yeah, and in terms of 5G materials, there are a few issues that we're starting to see being seen by our customers, and it's giving us an opportunity to develop new materials. One of them being the K-Zorb material. So fairly often you will use sheets of microwave absorber material, and they will need to be placed very close to signal lines. So, for example, in an antenna system, you'd normally put absorber material down, and this will be very close to traces on PCBs that are actually transmitting signals. One of the things we found is that with a very close proximity of the absorber material to a line that's transmitting a signal, it will actually cause the signal to have some issues. It will start degrading. So one of the materials we developed was called K-Zorb, and this is actually a flexible dielectric material that's sandwiched onto an absorber material. So this gives you the chance to place an absorber against a PCB, but there's actually some separation there, so it then doesn't affect the normal signals that are running in the trace lines. The second one we're looking at is, again, along the lines of the CoolZorb material. Typically this is in a sheet type of material that we cut into pads, and then it will be placed into cavities. One of the things we're looking at now is actually making a dispensable version of this. Technically it's a very difficult thing to do, but we're almost at the point where we have the material ready to be released to the market now. So this will allow customers to actually be able to dispense CoolZorb material directly into cavities in castings to be used in systems. So that's going to be a very big breakthrough actually for the telecom industry.
To paraphrase Henry Ford, going back 10 years, you could have absorber in any form you want as long as it was a flat elastomer sheet. But now it's dispensable. It could be moldable, it could be formable, shapeable, which is kind of what the industry is demanding. So we've come up with many different form factors for delivering absorber material and thermal material to where it needs to go in a cost-effective way.
What new products in the 5G area are you finding our customers are most excited about? And maybe you can tell us why.
It's probably the absorber materials themselves, actually, because this is something where traditionally they've been used in the telecom kind of industry, so usually around antennas or for cavity resonance in some of the baseband systems and things like that. For 3G and 4G, it was fairly easy to try and manage the kind of cavity resonance and crosstalk in antennas. With the rise in frequencies, that's now becoming more and more difficult. So actually the dispensed absorber is starting to look really attractive because the cavities are becoming smaller and smaller, and you have so many of them in one of the baseband systems that it's physically very difficult to actually place the pads within the cavities. So dispensing seems to be an ideal solution for that. So that's something that we're starting to discuss with customers, and it's already gaining some traction. The other idea is the textured absorbers as well. So again, it's possible to kind of tune absorber materials to specific frequencies. So that's something that I think is going to become more and more important as we move forward.
Paul and Matt, we're not done with the 5G area. It's still growing. So as we look to the future, what's your vision of the future of 5G? What do you see happening in terms of use of products and some of the challenges that we're going to help our customers solve?
There is a large opportunities out there in urban areas, in football stadiums, both American football and what the rest of the world calls football, to get high data rates and while watching a game. So those are some of the biggest challenges, and then simultaneously solving the thermal problems with the EMI problems, I think, is the biggest challenge. But I think these are all achievable. And then we'll just have to start getting ready for 6G.
Yeah, I'd go along with that. Probably one of the biggest issues that we're going to see with 5G is the actual range, and that's down to the physics. As the frequencies go up that are needed for the data transmission, the range that you can transmit the signals over goes down. So this is something that it's a physical limitation. The only way around it at the moment is actually to put more infrastructure in. So basically, the cells within the network become smaller, and you need more and more physical pieces of equipment within the network itself. So we're only at the beginning of the what's being known as the fourth industrial revolution. So this is basically the Internet of Things and the 5G and interconnected devices. We've got a long way to go on this. So the estimates I've seen, the 5G technology is set to peak by about the mid-2020s. So we still have quite a way to go in development on that. The 6G network system is being looked at already. And in addition to this, there are also new technologies which are coming along as well. So for example, the Starlink system by SpaceX, that could well turn out to be a game changer as it's providing satellite internet access globally.
And I think there's new applications that we don't even know yet. Virtual reality and augmented reality as well, where an overlay onto the real world sort of thing. I think there's going to be a lot of applications there. That requires the low latency, requires the data rate, and that sort of thing. And we can't even say what they are yet, other than in the abstract.
Well, thanks very much for sharing your insights with us today, Paul and Matt. It's a really interesting area. Devices are getting smaller. The amount of heat being generated is larger. The frequencies being used are higher. So it's just creating a perfect storm of challenges. But I know both of you enjoy solving challenges and working with customers to make the world a better place. So I'm happy to say you have lots more excitement ahead of you. So thank you. And to all of you for listening, thank you for tuning in to this episode of Insights Engineered. Please visit laird.com and follow Laird Performance Materials on LinkedIn to learn more about our latest products and innovation. Thank you.